Welcome back. And the topic this week is actually a continuation of where we were last week. And the idea is to go a little bit deeper into some of the more popular methods for finding roots of functions. And in our case, the root of the function is going to be the gradients of the energy which we're calculating. And we want to find the gradients of the energy as a function of the variational parameters. Now, there is a plethora of methods. There are many, many methods. So we have to, in a way, figure out which are the most relevant ones for the case which we have. Now, in our case, we are dealing with a multidimensional integral, which means, as we discussed last time, that some methods, like Newton's method, where we would require the calculation of the second derivative, which defines what in the literature is called the Hessian matrix. This is something which is not wanted from a computational point of view, because calculating the second derivative of the expectation value of the energy leads to 6, 7 additional integrals to evaluate stochastically. And if you're dealing with 10 particles in 3 dimensions, your integrals are 30-dimensional ones. And even if you do Monte Carlo calculations, these integrals will take a lot of time to evaluate. Now, what we want to do as well is to be able to obtain an estimate for the optimal parameters. That means where the energy has a minimum as a function of the variational parameters. We want to find an estimate as quickly as possible. The brute force approach is to sample with many, many parameters, a whole domain of variational parameters. But then for each set of parameters, we would typically spend millions and millions of CPU cycles. So this is a waste of CPU cycles. So the idea with using these methods is to find the minimum as quickly as possible through optimization methods. And then when we have found the optimal parameters, that is when we start the big Monte Carlo machinery. So there are methods in the literature like Broyden's algorithm and variants thereof, which are used. We have what we may actually end up doing, which is called plane gradient descent, alternatively combined with a variant of Broyden's methods. These are the methods which most likely we will end up using in this project. Then, for the sake of completeness, we are going to discuss one of the more popular methods, if you can calculate the second derivative. And these are the steepest descent and conjugate gradient descent methods. Now, for those of you who would like to explore neural networks in Project 2, then we would more dive into stochastic gradient descent. This is something which we will not cover now, but many of you have taken a course in machine learning, you have met this. Then, at the end of the lecture, we are going to return to the coding strategies, which we discussed last week. But today we are going to go through some of these more popular methods and look at their stabilities and their pros and cons, and what are the benefits and what are the cons against these methods. So that you, at the end, you have to make a basically you have to make a judgment and then pass this judgment and decide which method you want to use. But for project number 1, where we are going to have very few variational parameters, semi-Newton methods and gradient descent methods are normally those which we would end up using. Now, there is a link to a textbook here, which is the kind of standard textbook in the field. And they have a collection of lecture slides, which you may take a look at. Now, the interesting chapter here, just to guide your reading, is chapter 9 on algorithms. But let's bring back the whiteboard and remind ourselves of some of the things which we discussed last week. So before we jump into the Jupyter notebook again, we are going to just quickly remind ourselves of some of the technicalities. And then we're going to look at some simple cases and runs which we can make. and look at the pros and cons of some of the methods which we will implement. So let's do a quick reminder. What we did was essentially to make a Taylor expansion of the energy as a function of the variational parameters around the minimum. So last week, we had a Taylor expansion and the quantity around the optimal parameters. So we have an alpha hat. And keep in mind now that unless I specify it, alpha can be a scalar or it can be a vector. So from the context, you will understand whether this is a vector or scalar. So we had around the optimal parameters. So we were looking at the expectation value of the local energy as a function of these parameters alpha. And we made an expansion. So we actually defined this in a more compact notation as an E of alpha. And this was then given by a constant E of alpha of k plus 1. So this is iteration k plus 1, or just a value k plus alpha k plus 1. You don't need to think of this as an iteration. But you could just think of you making a Taylor expansion around that point, alpha, where you have the optimal value. And in this case, we got the second derivative of the energy. So we had a gradient of E, and this is calculated at alpha of k plus 1. Now, since this can be a vector, we have to take the transpose, that one. And this was multiplied with alpha minus alpha k plus 1. And then we have the second derivative plus, and then we had a 1/2, and then we had a vector alpha minus alpha k plus 1 transpose. And then we have the second derivative of E, calculated this alpha k. No, this is not alpha of k. It should be alpha of k. So, no, sorry, it's alpha k plus 1. Alpha k plus 1, like that. And this is again multiplied with alpha minus alpha k plus 1 plus higher order terms in alpha. So this is normally given by the norm 2 of the vector squared, alpha k plus 1. And this is norm 2 of the vector, but this is normally cubed here and higher order terms. So what we would typically do then is to truncate at the level of the second derivative. And when we did that, we obtained Newton-Raphson's method, which is then solved iteratively. And this is a typical technique you would use for nonlinear set of equations. So if you look at what we have here, this is something which is more, can be generalized. And what we did last week, and this is something which I will use now. So we generalized. Instead of having the energy as a function of this alpha, we generalize this to just a generic function f of x. And the type of equation which we end up with is an equation where we have a f of y, we make a Taylor expansion, but we have an f of x, a constant, plus the derivative of evaluated f of x transpose, multiplied with y minus x, plus 1/2 of y minus x transpose, multiplied with a second derivative of a function of y minus x. And then we truncate at the level of the second derivative. And we are also assuming that the second derivative is larger or equal to a constant, since this is now a matrix, multiplied with a unit matrix. And if you have the standard m equals 0 case, that is what you normally have for a convex function, so that the second derivative is larger or equal than 0. But this is one of the basic assumptions which we are making about the function. And if we then want to make this even more compact, we could just think of this in a more compact way. we could now just think of this as a function, f of x, which is given by some constant, because this quantity which you have here is actually a constant. This is something you have calculated. It's just a number. F of x, f of y is a scalar. So there's a constant plus, and then we could think of a vector, which we can call for B transpose times a vector x, which is the unknown quantity we want to determine, plus 1/2 times x transpose times a matrix times x. So the matrix A is now the same, which represents the second derivatives in our case. So for us, the interesting case is actually the second derivative, and this is the quantity which we normally want to avoid to calculate. So when we now look at this df of x, of d of x, we want that one to be 0. In this particular case, that leads to a standard problem, which you have seen many times, that a of x is equal to minus b, which in turn means that the x, the unknown quantity, is given by this standard linear algebra problem. Now, this is normally something you cannot do, because calculating the second derivative, which is now represented by this matrix A, is something which becomes computationally extremely expensive. And you would have to evaluate that for every iterative step, because the basic algorithm, which we end up with, is, and this is what we derived last week, this is Newton-Raphson's method. And Newton-Raphson's method simply says that we can solve in an iterative way, x of k plus 1 equal to x of k minus, and then we have this, is, in our case, this is the second derivative. But if we're just dealing with this function, what we end up with is now the inverse of f evaluated at x of k. So this is the inverse multiplied with f of x of k. So keep in mind that these can be vectors and matrices now. So the quantity which we have in this particular case, this del of f of ij, this is nothing but the derivative of this function with respect to one of the variables x of j. And this is normally called the Jacobian. Now, in our case, the function we want to drive to 0 is not a function f of x of k, but it's actually the derivative of the energy. So in our case, this f of x is equal to the energy derivative. So the gradient of the energy with respect to these parameters alpha. So that is in itself a vector. So what we get is that the quantity which we have here, which is defined as a gradient, is actually a second derivative. And that leads to a matrix which is called the Hessian, and that's the second derivative of the energy with respect to the gravitation, with the variational parameters. Now, the basic problem, or the problems which we typically face, and the drawback with Newton's method, is actually you need to compute the second derivative, or the Jacobian. That's one of the drawbacks. And one of the other ones is that the convergence of this iterative process depends very much on where you start. So you should have a guess for your iterations, which is pretty close to the optimal value. So the drawbacks, just let us list them here. One, we obviously have to calculate this gradient. So we need f of x evaluated at k. In our case, it's a second derivative. A second derivative, which in the Monte Carlo calculation leads to an integral or 7 integrals, which are multidimensional. So this is something which we obviously want to avoid. So the other thing is that it depends, it's very sensitive to initial values. Of the iteration. And this value could be some kind of value x0, which is just the initial guess. So you would typically guess, and if you have an understanding of where the minimum is, then you may come with a good guess. Else, it may take a lot of time before you converge. The other thing is that these kind of methods can easily bring you into a local minimum. Now, we are pretty lucky in this project, is that we have essentially a function which is nice and convex and has a global minimum. And you have probably seen that when you plot the energy as a function of the variational parameters alpha. And you saw that also with the case of the 2-electron problem, where we have two variational parameters, there is a nice minimum. Now, when it comes to many of these strategies, because at the end, we have to choose one initial value for the parameters. What is commonly done then is that you run a cheap Monte Carlo calculation. So when I say cheap, you run a calculation with a few Monte Carlo cycles, and then you plot the energy surface, or the energy as a function of the variational parameters, just to get a feeling where you roughly have the minimum. So when you have nailed down roughly where you have the minimum, you would then start this iterative process to fine-tune and find the minimum. So this is very typical for many of these Monte Carlo calculations, that you run a preliminary calculation with few cycles just to get a rough image of where the minimum may be. And then, instead of just guessing randomly and starting your iterative process at a random point, you would start your selection of the random points in a more intelligent way. So the first simplification which we are going to encounter is what is called the plane gradient descent. That is just the gradient descent. And many of you have met that if you've taken a course in machine learning, for instance. And in that case, what we have is that x of k plus 1 is equal to the previous value minus, and then we have a constant gamma here. And this constant gamma can depend on k, or it may just be a constant throughout the calculations. And this is then multiplied with the function value which you have. So this is our f of x of k, which in our case is actually the gradient of the energy with respect to these variational parameters. So in our case, what we have is a variational parameter, alpha k plus 1 equal to alpha k minus of gamma of k multiplied with delta E of alpha. So this parameter is often, if you do machine learning, this is called the learning rate. Now, if you can diagonalize that matrix A, which we call the Hessian matrix, so if we can diagonalize A, then you can actually show that this gamma of k should be smaller than 2 divided by the largest eigenvalue of this matrix A. So that's a mathematical requirement, which I'm just stating, but which you can find in that textbook by Boyd and van der Hagen, the one which I mentioned in the beginning of the lecture. So if you can diagonalize, you can do that. Else, what people would do is simply to make runs with the different selections for this parameter gamma. Now, we can be a little bit more ambitious. And one of the simplest ways to update this gamma is now to use what's called the second method. And many of you may have heard about the second method. So let's look at a further complication, but which is one of those which we will base our next implementation on, which is called Broyden's method. So let's discuss Broyden's method, which is a way to find an estimate of this parameter gamma of k as a function of the parameters which we have in the iterative process. So Broyden's method, and the one which we will use is normally called Broyden, Farberg, and then I think it's G. Goldberg and Shano. That's the acronym for the different authors which developed that one. But in order to look at that one, we are going to now first look at the standard secant method. So let's now look at the secant method first. And some of you may have encountered that in different courses in computational science. So if you did a course in numerical mathematics and you studied root finding methods, the second method is actually a very straightforward one to implement. And it's based on you assuming that you can interpolate from one point to the next one with a straight line. So the secant comes simply from the word that we are approximating this gamma of k with the secant itself. So then we assume that the function we are interpolating between 2 points can be represented by a polynomial of first order. So let's look at the second method first, because that one is the one which is used in Broyden's method. So when we look at Newton's method, what we are doing is now the following. So I'm just going to repeat some of the basics here. So Newton's method, that transforms, what it does is to transform a equation where we want to find the roots, f of x, into what we normally called in mathematics a fixed point problem. And that fixed point problem is then given by some function x, which is given by g of x. And this function g of x is nothing but the method which we implemented in Newton's algorithm. So which is f of x divided by the derivative of x. So we have translated a root finding problem into what's normally called a fixed point problem, where the function which we want to use, this g of x, is now simply given by what is given by Newton's algorithm or Newton's method. And that means that, and hence, what we have then is that this g, the second derivative of x, is actually equal to f of x, and this is just a simple application divided by this, divided by the second derivative squared. So if we have just one root, so if we find a specific root, if x star is just a simple root, then this function, the first derivative of this function g has to be equal to 0. And then we say that the convergence rate is quadratic. And the iterations have to start close enough to a root in order to converge. So if x of x is a simple root, then this g with this x of x is actually equal to 0 if this f of x is then equal to 0 and the first derivative, as you can see from the equation we had on the previous slide, is not equal to 0. If that is the case, then we say that we have a quadratic convergence rate. Okay, so if we look at the second method, the thing is that for each iteration, Newton's method requires that we can calculate the derivative. So Newton's method requires that we can calculate, we have to calculate actually, so we need to calculate f of x at a given iteration k, x of k, and the derivative, which in our case is the second derivative. And this may actually be, as we've been saying, but this may be expensive computationally, and in some cases it's not even feasible because we may have tons of parameters which we want to optimize, and then the matrix which we end up with is just a monstrous matrix. And that means that it simply becomes computationally infeasible. So in the second method, then we have a very simple expression for this equation. So in the second method, and this is one of these basic methods which we use to find the roots, and you probably have encountered the bisection method as well, which is even simpler. They do actually converge to the final root, but they may take a lot of time to converge properly. So in the second method, the derivative is approximated, and you will not be surprised to see the way you approximate it, is approximated by the finite differences. So we have the f of x of k is simply given by f of x of k minus the previous value, minus 1, and divided by x of k minus x of k minus 1. And I guess you've seen that formula before. And I hope you don't get offended if I repeat something which is that simple. But this is essentially high school mathematics. So that means that you would then change the method. So you would have something which would be linear in x. So we get an x of k plus 1 is given by x of k minus, and then we have the function itself, and this is then multiplied with x of k minus x of k minus 1 divided by f of x of k minus f of x of k minus 1. So this is one way to perform these calculations. Now, what you can show then is that this convergence rate is a little bit worse than quadratic in the error which we have, which is the difference between the previous value of x and the new value. That's how we define the error. So Newton's method is quadratic in that. So that means that the error becomes smaller and smaller. Whereas this one is a little bit more than linear. So we normally call that superlinear. But it has a weaker convergence rate than Newton's method. But this is a pretty straightforward way of implementing the gradient descent. And this is one of the methods which you can think of using instead of just having the constant learning rate. But then Broyden came with an approach back in the 60s, which is a little bit different. So in the Broyden's case, what he did, algorithm, in what we are going to do then, if we are now looking at the Jacobian, which we have to calculate, if we have x of k plus 1, so let's do a slight rewrite. So we are now going to write the first derivative, since these are not necessarily just scalars, but it can be a matrix. So what we have then is the Jacobian, which we defined earlier, multiplied with f of x of k. So I'm writing it like this now because it can be a vector, and the Jacobian is a matrix. So as long as j of x is not singular, this is another problem which we have to consider, then the convergence is actually quadratic. But as I said, computing the Jacobian has a cost. If you think of this one, which is now a matrix, so this has a cost of, if you now assume that the Jacobian itself is a real matrix and a square matrix of dimensionality n times n, that has a cost because you need to calculate the derivatives of n squared floating point operations. Floating point operations. That is to set it up. But then we need to invert it, plus matrix inversion, which then accounts to something which goes like n cubed floating point operations. So that means that this becomes actually pretty expensive. Floating point operations. Or just flops, as we call them. So in practice, we do not normally explicitly invert this J, the Jacobian matrix, but we actually solve a linear system of equations. So normal not to solve the matrix, not to invert. But what we end up is to solve a different problem, but solve a problem where we have a J of x of k multiplied with a quantity s of k, which I'm going to define. And this is given by minus f of x of k. So just keep in mind what we have. So we have an x of k. Let me quickly remind you of that so that you see how this comes through. So we have a j minus times f of x of k. So what we're going to do now, instead of doing the inversion here, we are going to define a parameter, s of k, so that x of k plus 1 is actually equal to x of k plus this s of k. So if you look back at the equation here, you see now that this quantity is the same, this quantity here is the same as this s of k, but multiplied with jk. So if we just invert that one, then you see that s of k is given by this quantity here. Okay? Now, the Broyden's method is actually based on this updating of the second, but in a slightly different way. So the algorithm, the way it proceeds, is as follows. So you would typically define an initial value, x0, and an initial value for the Jacobian. And I'm going to give this a name, and I'm going to call this B0. So that's the initial values, which we need to define. So you could have a guess for the Jacobian, where you just put that one equal to something along a diagonal. And that is a pretty common guess. So instead of having a matrix with which is dense, you could simply have only values along the diagonal. And these values could also be initialized with just random values. So you would do that, and then you would then have a loop here for k equals 0 to max iterations. And then what you would do then is first solve the equation where you have b of k times s of k is equal to minus f of x of k. Then when you have solved this equation here for the unknown s, then you get the next update, x of k plus 1 equal to x of k plus this s of k. I then define a new quantity, which I call y of k, which is simply given now by the x of k plus 1 minus f of x of k. And then we can show that the next step of this b of k plus 1 is given by the previous value. And now I'm just using the second, but I have to explain to you how we use the second in just a moment. So I'm just setting up the algorithm here. So this is given by plus, and now comes the expression which we are plugging in. So, and the expression is given, is based on the second, which we put up earlier. So we have this y of k, which now contains the difference between the function values. And then I have minus this b of k times this s of k multiplied with s of k transpose. And this is then divided by s of k transpose times s of k. So this is the way we are updating that function b of k. And this is the end4. Now, what is done and how we actually arrive at that equation is to consider a following approach here. So when we now are computing that equation, so we have an equation b of k times an s of k, which is equal to minus f of x of k. What we are making as an assumption is that this b of k plus 1 is equal to the previous value plus a matrix c of k. Now, this matrix c of k, that could simply be given by the second, as we did before. If it was a second, it would just be a vector in that case. So this quantity which you see here, this is what we are having here. Now, that means that you can make a model. And the way you approach this quantity can be done in many, many different ways. So the simplest one is what is called Broyden's modification of the second rule. So what Broyden did was then to assume that this c of k is given by u of k. So keep in mind now that these are matrices. So there is a vector u of k, which is undetermined. And this is multiplied with the vector transpose. So if you look at this quantity transpose, which we have here, this comes from us defining an outer product. So remember now that this is a matrix and it's an outer product, okay? So this u of k is undetermined. So we need to find a recipe to define that one. So this is one way to make a model for that update matrix, okay? And the way you do this leads to different types of complications. The simplest one is actually Broyden's method. And what you can show then, if you use the second method, and I leave that as a little exercise to you guys, it's not that difficult. Second method, you can then show that this u of k has to be equal to y of k minus b of k times the original s of k divided by s of k of t times s of k. And remember now that this s of k was the same as x of k plus 1 minus x of k. So we have that in the denominator. So this is a modification of the second rule. So if you use the second method, if you do that, if you now look at y of k, so y of k, just let me quickly remind you, is given by f of x of k plus 1 minus f of x of k. So what I've done here is a simple modification of the second rule. Because then you see that you have parts of it here, this one is here. And the way you implement this is simply to assume that when you perform these operations, you are now assuming that this x of k plus 1 minus x of k transpose times this quantity u is equal to 0. So which means that what you're saying then is that the b of k plus 1 times u is equal to b of k times u. If this is the case. So this is an assumption which you make in order to set up this iterative process. Now, there are many, many different variants of this. And the one which you will often see being used is a further modification of Broyden's method, which is called Broyden-Fletcher-Goldfarb-Shannon, which is one of the parameters we have in this the SciPython package, this optimization package. You would simply call that one with an input parameter, which is called BFGS, and that is the code which we discussed last week. So I'm just going to set up the basics here. So in this Broyden, and then we have Fletcher, and then it's Goldfarb. Channel, and this is often shortened to BFGS, and you will encounter that in the literature. In that case, this update takes a different form. Update. And I'm not going to derive it, but I'm simply going to state it here because you can choose the kind of updates you want. You can make them more and more complicated. So you have plus, and there's a parameter A. You have U times U of T plus a new vector V times a vector V of T. And these are unknown quantities which need to be determined. And then you can show that this B of K plus 1 is equal to a B of K minus, and I'm just setting up the final expressions here. And these are the expressions which are encoded in these libraries. So B of K, so this gets a little bit more complicated, and you see quickly why you don't want often to use these methods. Now S of K plus a Y of K, which if I've written everything correctly, divided by Y of K times this quantity S of K. So I'm not going to go through the derivation, but you're putting in a similar requirement as we had in the previous case with that vector U. So you can make, the whole point is that you can make different models for how you update these gradients. So let me quickly remind you. So the simplest way you can do this is to replace this gradient with a second method, which means that you simply have this expression here. This works well if your function f of k is close to a straight line. If it is a straight line, that means that f of k is a first order polynomial. The second method works very well. But in general, we are not that lucky that we have first order polynomials. Normally the functions which we have to optimize are higher order polynomials. And that means that we need to find a way to improve this update without having to calculate the gradient. So everything here now rotates around us trying to avoid to calculate the gradient. So there are different tricks. So one trick, which was invented by Broyden back in 1965, was simply to assume that you can update your gradient, so this function b of k, which is now proportional to the gradient, but simply update that with a new matrix, where this new matrix is given by the outer product of something we know with an unknown quantity. And then you use the second method to find this quantity u of k with the assumption that this u is orthogonal to that difference. So these are assumptions which you can impose, because that means that these expressions here has to be fulfilled if this is the case. Now, there are many, many different ways of doing this. And what Broyden and company proposed afterwards was to make it a little bit more complicated with the two unknown quantities. You can add more and more such unknown quantities. But what you end up with then is a more and more complicated expression for the gradients. In our case, the gradient is the second derivative of the energy. And we don't want to evaluate that simply. And this means that when we now, after the break, we are going to look at some other ways of solving this problem. But all these methods rotate around either you being able to calculate the gradient or making approximation to the gradient. At the end, what many of you will end up doing, and that is what many practitioners actually do nowadays when you have many cycles you can waste, is simply to implement the plane gradient descent. And this is the most likely implementation which you will do. We do, however, have the possibility to implement this modified Broyden method. There are libraries in C++ and Python as well, and Fortran, which allow you to implement those methods. And at the end of the next lecture, we are going to look at the two strategies. One, where you simply implement this one, and two, where you implement Broyden's modified method. And these are available methods for you. These methods are okay as long as you have few variational parameters. When you're getting into many, then you would often just revert to this one and find ways to modify and update the learning rate. So methods like adaptive gradient, root mean square propagation, which many of you have heard of, are actually inspired by Broyden's method, which are then modifications of the second method, where we try to give approximations of the gradients. So I hope you see the kind of overarching picture. And after the break, we are going to look at two other methods, which we will not implement, but we are going to include them for the sake of completeness, because these methods are widely popular if you're dealing with optimization problems, and you can invert the matrix A. And these are the steepest descent and the conjugate gradient method, which is a beautiful method. But we will not use them because they require that you can calculate the second derivative of the energy. So a little bit now is for us to navigate the landscape of all the methods which are available. And at the end, we will end up picking the simplest possible one, because that's the one which is easy to implement and at the same time saves a lot of CPU cycles. So even if we're going through all these types of manipulations, at the end, will often be stuck with some of the simplest possible methods. And what I want to do now after the previous lecture is to say something about two very popular methods. One is called the steepest descent, which is also widely used. It's a modification. It's not the same as gradient descent, but it's a better implementation because it allows you to update that parameter gamma of k every iteration. But as you will see, these methods require that you can invert the Jacobian matrix and calculate the Jacobian matrix. If that is the case, then I would normally recommend to use those methods. But that means that you have a kind of problem where you can pre-calculate the Jacobian matrix. So if somebody here has followed a course on machine learning, and if you think back to a method called least squares, in the least squares case, you can actually pre-calculate this matrix and then store it and calculate the inverse of it. Yeah? Yeah. Yeah. So the advantage, if you will see that quickly, because if you have Newton's method, this is just the implementation of Newton's method, then you have an exact expression for this gamma of k. So the advantage then is that you will see that the convergence is very rapid. Whereas in general, we don't have a proper expression for this gamma of k. And we would like to avoid to calculate it, because in our case, you end up having to evaluate multidimensional integrals for the second derivative. And they will have a statistical error because they are determined stochastically, which again means that even if you run it with as many cycles as you want, it will have an error. And the second derivative will be a sum of many different integrals. And the way you sum them up can also lead to errors, because you will have errors in every. So let's take a look at one of these very popular methods, which is called the steepest descent. So let's go back and let's go to the end here and simply introduce the steepest descent. And the algorithm here is actually also pretty simple. So everything is based on us having a type of problem where we have a function f of x, which is given by some constant plus 1/2 of x of t times a times x. And whether you put a minus sign or plus sign in front of the next term doesn't matter. But now for the sake of simplicity, I'm going to put a minus sign. So if I then, so this b is known. And the same with this one. And x is the unknown. So known means we can calculate it, or it has a fixed value. And in case it has fixed values, this is where methods like the steepest descent and the conjugate gradient come to play. This is not what we are going to have. Because in our case, coming back to your question, Luis, is that this function here is not going to be a constant, this matrix. And this one is not going to be a constant either. So this will be our gradient, which depends on a given value x of k. And this a is going to be the second derivative, which depends on the values x of k. But as we discussed before the break, when we take the derivative and we want that one to be equal to 0, that leads to a famous equation which looks like a times x equal to b. And we know how to solve that one. If we can invert the matrix, so we're assuming that the matrix can be inverted, but the general way to solve it is to solve this in an iterative way. And the way we would solve it iteratively is first that we define an initial value, x0. We would also define what's called the error. Or what you might call the reminder. And we are going to call this for an R of iteration k, which is going to be given by a times x of k. So let me just rewrite it in a different way. Doesn't matter actually, but it's easier to deal with. D minus a times x of k. So that means that every time we update x, we can calculate the difference between the approximation x of k and the values which we want to have, where what we want to is that this quantity should be equal to 0, right? But since we are solving this iteratively, we may not have 0. So that defines an error or reminder in every iterative step, okay? Then, when we are setting up the algorithm, and the algorithm is extremely simple, and we discussed that and a slightly different way of defining that last time. So we would now define, or we would have a for I equals 0 up to max iteration. And we would then define a new quantity, which we call now for R of k, or x of k plus 1, which is equal to some alpha of k times some R of k. And then we can update R of k plus 1, which is then equal to b minus a of x of k plus 1. Now, if you look at, so this is basically the algorithm which we are going to implement. If you look at what we have, we need to find an expression. So here we haven't defined what alpha of k is. So how to find alpha of k? So we need to calculate that one. because else we cannot perform this iterative process unless we put alpha of k to a constant. Sorry, I also forgot. So this should be given plus an x of k. So this is the expression which we want to code. So we need to find alpha of k. So if we now look at the iteration, which I call x of k plus 1 equal to x of k plus this alpha of k of r of k, the remainder. This is very similar to what we did before the break with Broyden's method. So in Broyden's method, we had a matrix which we updated as an approximation to the derivative. We had the previous value, and then we made an assumption about how the remainder develops. And this is actually going to be proportional when we look at the Newton's method with the gradients. So we can rewrite this as just b minus a times x of k plus alpha times r of k here. So I'm just rewriting the expression because my x plus alpha r of k is something which I can just rewrite in this way here by introducing b. And then what we have then is that my r of k plus 1. No, sorry, I actually did an error here. I was looking at the wrong line. Please excuse me here. Sorry. It's r of k plus 1, which is equal to b minus a of x of k plus 1. And this is what we can rewrite as a b minus a. And then I can write this as an x of k plus an alpha of k of r of k. Sorry for that confusion in the previous step. Then I can now reorder. So what we get then is, when we look at this expression here, if we now take r of k plus 1 and look a little bit more carefully at the expression which we have, and then keep in mind that what we can do then is that we are assuming now that this is orthogonal r of k. So if I am going to multiply with the r of k transposed on the right-hand side, then what I'm going to get then is the following. So if I multiply with r of k plus 1, we get that one equal to 0. And if I then collect the terms which I had on the right-hand side, this is going to give me an r of k transpose times r of k is equal to r of k transpose times alpha of k of a times r of k. And that leads to an expression for alpha of k, which is simply given by r of k transpose times r of k divided by r of k. And this is the same expression which we derived last week in a slightly different way. So then we have an expression for alpha of k, which we then can use to update x of k plus 1. So then we get x of k plus 1, which is simply equal to x of k plus this alpha of k multiplied with r of k. And this is pretty easy to implement numerically, and this is what we are going to look at now. So the numerical implementation is something which we have in a Jupyter notebook here. So if you're okay, yeah? No, the b is just a constant. So this could be, in our case, it can be the gradient. But as you will see now when we look at the examples, so let me just go into the Jupyter notebook. And we are going to look at a simpler case. So what you will find first is just a reminder of the convex functions, etc., etc. So this is just the basic mathematics which we have implemented now. But we are going to look at this example here, which we discussed last week. And now you see that this is an equation. If you look at this function, which depends on x1 and x2, we can rewrite that function in terms of a vector x, which is just x1, x2, a matrix A, which is this one. So if you perform the vector matrix vector multiplication, you will get x1 squared, x1 times x2 times 10x squared, x2 squared. And then you have this vector B, which is just 5 and 3, which when it's multiplied with this one, just gives you minus 5 times x1, minus 3 times x2. That's okay? So this is just a typical example of a function which depends on two variables. But keep in mind now that in our case, this is known and this is known. In our applications, B is going to be the gradient of the energy, and A is going to be the second derivative of the energy. And then you see clearly that these are things we don't want to evaluate because these quantities are given by multidimensional integrals. So if you look at the straightforward way, is simply now to require that this gradient is equal to 0. That means that you get AX minus B, and you can then here easily invert the matrix, or you can simply just write it out for each x1 and x2 term. And if you require that one, you get an equation which is pretty straightforward to solve, and you find these equations here. These are the analytical equations. Okay, any questions so far? So this is just another way of rewriting it, but just keep in mind now that in our case, this is the second derivative, and this is the gradient. So if you then look at a simple implementation, this is now the plane gradient descent. So first we set up the matrix. We have defined the derivatives and the function. Now, one of the things I do now is I use the eigenvalues to define the learning rate of this parameter eta. And here I'm doing a pretty stupid thing. I'm simply now just setting a constant, and I just write 100 iterations. There is nothing elegant here, yeah? So that's a very important point. But in this case, for the 2x2 matrix, this is a trivial thing. But if you have a big matrix, it takes a lot of time to find the eigenvalues. So that means that you would actually abandon this approach, and you would rather simply just set it to, let's say, 0.01 and do something like that. Or just play it. Yeah. Normally, you don't have the possibility to calculate the eigenvalues. But now I'm just using the criterion for convergence here. And if we now also print the gradients, so let's do that. So these are the two gradients we are going to print. What you will see here with 100 iterations, this is the exact solution which we should get, these two quantities. This is 1 divided by 39, and this is 97 divided by 39. And you see now that the gradients start being large, and then slowly, after 50 iterations, they're slowly moving towards 0, but very slowly. And now, at the end here, we have a solution. So you see the gradients are 10 to the minus 4, 10 to the minus 5. And this is the relative error. So the first one, which was 97 divided by 39, I have a relative error, no, absolute error. This is the absolute error, 10 to the minus 4 and 10 to the minus 6. So here I just used 100 iterations. And clearly you can make this smaller and smaller. The code here is not very elegant because there is no, I haven't implemented any kind of, how to say, stopping criterion. I could just increase this one and I could rerun it. And if I do that one, you see I have a much smaller error. But now I did 1,000 iterations. So 1,000 iterations in our case, where we evaluate integrals stochastically, is going to take a lot of time. Now, the steepest descent, let's do that. So what I did here was to put in 30 iterations. And now I'm calculating the residual, as we did in the equations. I have an initial value, a random vector. I set up this quantity A times this R. I calculated the norm. And then I have my denominator, so I get C divided by deno. So this is the constant alpha. And then my update is simply alpha times this residual, exactly as we wrote in the formula. And then I calculate the residual again, or the remainder, which is simply A times X minus this B of T. So I just defined it with, instead of in the equations which we derived on the whiteboard, I have B minus A times X. So if I run it in this case, you will now see that I have an error, which is much, much better. I did 30 iterations, whereas with my learning rate, which I had here, I put 1,000 iterations now, as you can see. And the error is roughly of the same quality as you have here. So this method is superior to standard gradient descent, as you can see. But it means that you should be able to calculate the matrices which you have in the problem. And the same, you need to be able to calculate this vector B. Okay? So one of the next methods, and actually if you want to use this with C++, there is an example here. But then I wanted to say something about the conjugate gradient method, which is the superior method for this type of problems. So in the conjugate gradient method, what you normally do then is actually to use what we call conjugate directions. So keep in mind that when we did the steepest descent, we were then assuming that the vector in iteration k is orthogonal, this remainder is orthogonal with the vector which you update. So that means that this remainder will keep making these kind of orthogonal vectors as you move on step by step. Now here, on the conjugate gradient, you're simply using or performing searches in various conjugate directions. So the steepest descent can actually converge slowly because you're just putting vectors which are orthogonal to the previous remainder. So the whole thing here is that two vectors are conjugate if they are orthogonal with respect to this inner product. So if you think of the eigenvalues of a Hamiltonian problem, or the eigenvalue, if x's are the eigenvalues of this A, and the eigenvectors, then you know that this actually applies. So suppose now that x is an eigenvector of A, and the same with that one, then you know that this one multiplied with that is a constant times the vector, and then you have immediately the orthogonality requirement. If these vectors are eigenvectors of this one. So what you do then is actually to use this property of conjugate gradients, and then you, if you now look at the iteration which we are going to do then is to assume, as we did in the steepest descent, that there is some kind of remainder here multiplied with some parameter alpha. We assume then that this P of I is a sequence of n mutually conjugate directions. So in a certain sense, we are assuming that this forms a basis. And that basis is something which we can expand this quantity in. So we are then making an assumption that we can use this basis to expand the solution in. And then what we're doing then, if we are able to expand it in terms like that, we actually end up with A times X being given by this linear product here. And then we multiply with that vector from the left, and that gives us this property here, where we have this P, K of T transpose times B multiplied with that one. And then we can define the coefficients in terms of that. By doing this, we would typically start with an initial guess. We have a vector z here, which is just the difference. So this defines a kind of reminder. And then when we do that, we keep updating. We find this reminder like this. And we can define these vectors in terms of the reminder. So this is a little bit more complicated than the steepest descent, but the philosophy is not that different. And then by doing some algebra, we can then compute the residual iteratively. And this equals to this quantity or that quantity here, which then gives us an expression in terms of these conjugate vectors. So these are orthogonal vectors which we have constructed. It's not so difficult to do this. It's much the same as we did with the steepest descent. Now, if you now look at the implementation here, we are now looking at the same problem. So we define this vector r. We define a new vector v, which is just temporary constant. So we have an initial vector which we choose. And then we simply implement the conjugate gradient method here in these different steps. Is a little bit more computational intensive than the steepest descent. But if you run it, you will now see that with 30 iterations, we have an accuracy of 10 to the minus 15, which is basically numerical precision. So this method, if we compare that with the standard steepest descent for the same type of problem, that gave us an error of 10 to the minus. So we're actually dealing with 3 orders of magnitude improved errors. This is the absolute error. Yeah. I just have to take off this because I don't get it. So A, in this specific case, A is now matrix which we have. So if you go back to the problem, so in this specific case, A is given by this matrix. So we have this function. This is the function which we start with. And I didn't write. Well, I did have. No, I do have B actually. It should be. Yeah. No, that's fine. That's fine. I mean, it's the. So this is just a simple example of yeah. 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 So in general, I'm just setting up these methods in case you have the possibility to calculate these matrices and vectors in an easy way. So just keep in mind now that in our problem, this B is the gradient of the energy, and this A, which we call the Hessian matrix, is the second derivative of the energy. So these methods just outline a whole set of methods which you can use in order to find the roots of functions. So what I wanted to use the rest of the lecture now is to go back to our problem. Because in our problem, what we will end up with is to implement simply something like the simple gradient descent. Or we can use Broyden's method in case we can calculate the derivatives in an easy way. So let's take a look at some of the drawbacks of the gradient methods which we have. So if you use this kind of gradient methods, which is what we will end up using, the plane gradient descent. This is, if it converges to a local minimum or energy function. The problem is that if we have rugged landscapes with many local minima, this can lead to a very poor performance. In the project, which we have essentially one parameter. So this begs almost us for using something like a plane gradient descent. It's, however, sensitive to initial conditions. But if you think of the project, when you run the calculation for the non-interacting case, then you know the exact answer. And then you know that your parameter for the harmonic oscillator is equal to 1. That's where you have the minimum. So if you add an interaction and have a correlated wave function in addition with no parameters, you could start with the variational parameters close to 1. So then you have a physical insight about how to start the iteration. But in general, it's very sensitive to initial conditions. And then it's, as it says, it's very important to think about how you initialize the training process. They are, as you will see, they're computationally expensive to calculate. And if you're dealing with machine learning or statistics, the function to optimize is a sum of many terms with one term for each data point. And that becomes time consuming in addition. It's extremely sensitive to the choice of learning rates. So you may not know what is a best learning rate. And it treats all directions in parameter space in the same way, because you often have just a constant parameter gamma or alpha, as we called it. And it can take, if you're stuck in a saddle point, which will not be the case in project 1, then it can take a long time to escape the saddle point. There are codes from numerical recipes in C++, which you can also access. There is a, if you click on the link here, you will find these codes. And in that case, if you want to write in C++, this is an implementation of Broyden's method in C++. But we can discuss that during the lab sessions. But let's take a look at what we have to evaluate. So the equation which you see here, this is the derivative of the energy with respect to the variational parameter alpha. So we need to evaluate this integral. We need to evaluate this integral and that integral stochastically. So the first code example, as we discussed last week, implements plane gradient descent. Nothing but that. And what you need then is, in addition to, so this is the case for 2 electrons, but you can now take away the interacting part of the wave function and simply replace the harmonic oscillator part here and just use that one in your case. So I have the wave function, the ansatz for that one. I have an analytical expression for the local energy. And then I have a derivative of the wave function, which I need in the expression here, because this is a derivative of the wave function. This is a derivative of the wave function with respect to the variational parameters alpha. So we need, since we normally have analytical expressions for these parameters, for these wave functions, we can often find an analytical expression for the derivatives. If not, we would use automatic differentiation with either AutoGrad or JAX if you're dealing with a Python implementation, or you can use AutoDiff with a C++. But in this case, we have the analytical derivatives. I have set up the quantum force, and now I'm going to calculate these 3 integrals which you have here. This term, this one, and that one. And that's going to return the derivative. So if you now look at the standard approach which we have here, I'm setting up the derivatives. I'm performing a Monte Carlo calculation where I now run over the variational parameters. So what I'm doing here is to find the minimum with few Monte Carlo cycles. And when I found these minimal parameters, the optimal parameters, that is when I will launch the big Monte Carlo calculation. So here, I'm running a cheap calculation. I have only 10,000 Monte Carlo cycles. So this calculation is pretty cheap. And then when I'm done with that, I calculate these derivatives. So this is the energy derivative. No, the energy. This is a derivative with psi, delta psi. And then I bring all these terms together, and I have then the expression for my total derivative for psi times E. And this is now put in here, minus delta E psi, the derivative with respect of the wave function with respect to the parameters, multiplied with the energy. So this is my implementation numerically from Monte Carlo evaluation of these three integrals which you see here. And this is then returned. And when I return it, I now calculate everything through a gradient descent. And as we discussed last time, when you print the derivatives here, you will see that the derivatives are not exactly equal to 0 after 50 iterations. So this is just a stupid brute force implementation with no stopping criteria, no nothing. And then I just fixed a learning rate of 0.01. So this is a parameter you would then tune. So if we run this one, so let's just redo that. And this is going to take a little bit of time. Now, when you now use Broyden's algorithm, you need to set up a function which calculates the energy, but you need also to provide a function which calculates the derivatives. So you can see here, these are now the optimal parameters for, in this case, alpha. It's not 1 because I have an interaction. And then I have the parameter beta here. And you can see the values of the derivatives, they are not exactly equal to 0. But you would like them to be 0. So this means that you need to play around a little bit with these parameters. When you have these parameters, you're going to launch the big Monte Carlo calculation. And the next thing we are going to add is the calculation of the standard deviation in the best possible statistical way. And that leads to resampling techniques, which will be the next element you will have to include in your code in order to calculate the standard deviation the best possible way. Now, in Broyden's method, you will see now that I have the same things, local energy, the derivative, quantum force, etc. But now I need to provide a function which calculates the derivative of the energy. And this is done by essentially the same recipe we had before. But then you need also a function which returns the energy. So Broyden's method, which is this minimization algorithm here, and then I have Broyden and this acronym which we discussed before the break. I have a function which is called the derivative, and I have a tolerance of 0.14 here. So if I rerun it, you will see now that this one is going to need some few iterations in order to converge to the correct value or to the best possible estimate. So you see in this case, it used 3 iterations. It gives an energy which is basically close to the other one, but it gives you slightly different parameters here. So this is a better way of finding these parameters, because in the previous approach, so this implements now Broyden's method. In the previous approach, what we did was just a plain brute force gradient descent. So if I were to change this one, suppose to 0.1, I wouldn't get the same result. So let's see what happens here. So in the previous case, which is more brute force, you would have to tune this parameter gamma here, or eta as we call it. I think I called it eta, yeah. And in equations, it's called either gamma or alpha. But in this case, now I just increased it. So that means you're going to make larger jumps. In this case, we get a value which is still decent. And you see now that the derivative is actually better. So 10 to the minus 1 is a better choice than 10 to the minus 2. If I make it even smaller, you will see then that you will barely move. So let's see what happens then. You saw now that the derivatives were actually 1 order of magnitude smaller. So the first approach which you see here is the simplest one to implement. And I normally recommend doing that. And then when you have things working with the derivatives, you can then think of implementing Broyden's method, for instance. But these are the two recommended methods. So you see now the derivative is actually 2 orders of magnitude larger than we had in the previous case. The exact energy is free, and you don't get that here. So some people rerun these calculations and then find the best possible parameters. That means where the derivatives are as close to 0 as you can get, or are willing to perform calculations of. And then when you've done that, you would simply plug these parameters in your large Monte Carlo calculation. And this is our next ingredient in the setup and development of our code. And when we do that, we will also use resampling techniques in order to calculate the best possible error on the Monte Carlo calculations of the energy. And when we have all these ingredients, we have essentially all the ingredients which are needed for project 1.